I start? Uh, so, uh, Good afternoon. I'm going to continue the lecture. So we start with brittle fracture. So what is brittle fracture? It is the fracture of a material when material without appreciable prior plastic deformation. Brittle fractures that occur in surface are are either initiated by the defects that were present during the manufacturing or the fabrication processes, or by the defects that developed during service. So during the World War II, the first ships were all welded, and there were flaws in welding, so brittle fracture was a common thing. Uh, Although brittle fracture is less common than other types of fracture, it is more severe, so it can cause more damage. Uh, and brittle fractures typically travel very fast, and they absorb very little energy and can occur very fast. For example, in steel, the speed can be up to 2100 meters per second. Uh, Next, rivets. A rivet is a permanent mechanical fastener. It was there. Rivet was the most commonly used structure historically for ships, and it consists of a cylinder, and one end of the cylinder is the head, and the other end of the cylinder is called the tail. And on installation, the rivet is placed on the drilled or punched hole, and the tail part is bucked, which means that it expands to about 1.5 times the diameter of the cylinder, and it also becomes a new head. So the rivet is now fixed in that structure, and it keeps the whole structure fixed. uh, since And now the rivet is of dumbbell shape because there are two heads. First, since now there are two heads, the first, to differentiate between the two heads, the original head is called uh, factory head, and the newly formed head is called the shop head. Because there are effectively two heads, rivets can support tension loads, but the most common purpose of rivets is to support shear loadings. Hull failures. The picture illustrates wartime hull failure. Hull failure is what is hull failure? It is failure in the main body of the vessel, which is supposed to protect the whole vessel from water income or structural damage. Uh, a failure in vessel's hull can lead to more significant damage. So this is the reason why immediate action should be taken when there is hull failure. Uh, a common warning for a possible hull breach can be unusual collection of water on the deck and the slowage of rolling period of the vessel. Hull failure can be due to corrosion or fracture, which itself can be due to collision, overload, or contact or grounding. Uh, okay, next. So neutral axis is an axis in the cross section of the beam, which does not have any longitudinal stress or strain. And if the beam section is symmetric, isotropic, and is not curved initially before it bends, then the neutral axis coincides with the geometric centroid of the beam. And there is this property, all fibers on one side, for example, in this case, the bending moment is upwards. So in this case, the property would be that all fibers uh, above the neutral axis are under compression. Uh, yeah, are under compression, and the ones below the neutral axis are under tension. Yeah. Uh, and there's one more thing that it is that the parts that are close to the neutral axis do not are under stress. So this is a serious problem for many cross sections, like circular or rectangular. The problem is that these cross sections use the material inefficiently, and many parts do not contribute to resisting the stress. This is the problem. So there is this inefficiency. Uh, yeah, this I explained. The neutral axis. Structural parts that contribute to the the members that the parts that contribute to the structural strength are the parts that run continuously fore and aft throughout at least the ship's midship half length. So midship section is really crucial for determination of ship strength. And non-contributing structural members are the ones that run transversely, and the longitudinal parts that are discontinuous. Stiffness. Stiffness is a property that tells us how much and is an extent to which an object resists deformation under applied force. But this is different from elastic modulus, because elastic modulus is a property of a material, whereas stiffness is dependent on the dimensions. So it is more of a geometric property. For example, the axial stiffness for normal tension, for an element under normal tension and compression, is given by this formula. Yeah. So here this is Young's modulus, and this is stiffness. Then now bending stress. So when this bending stress, when the structure is under bending moment, under bending stress, there is essentially this intrinsic to this is generation of normal stress. So bending stress is a more specific type of normal stress, and the stress at the neutral axis, as we mentioned before, is essentially zero. So, but for example, okay, this is neutral axis, and this is the moment. The formula it is for the maximum stress, but it can be generalized for bending stress and stress that is generated under bending. It can be written this way as well. So at the neutral axis, there is no stress or strain, but so this is the deformed case for this. So as we can see, the lower part is under tension, the part below the neutral axis. under tension. And the upper part is under, the picture is bad, but get the idea. Uh, Under compression, the same here. So we can see that the stress depends on the vertical distance from the neutral axis. So we can deduct that the maximum stress can be obtained by using the distance, which is equal to the half of the height, and in this case it's from neutral axis to the top or to the bottom. So in this case, uh, uh, for this one, the maximum tension stress is at the bottom surface, and the maximum compression stress is on the top surface. And I is the moment of inertia, and this this thing is section modulus when you divide by, moment of inertia, second moment of area by vertical distance from the neutral axis. Uh, so a girder is a longitudinal member used in the construction of the bottom of the ship. And it can be placed right above the keel or to which is called center girder, and to the sides of the or spaced equally from the keel, and then is called they are called side girders. This is the midship section. So primary strength calculations generally require consider the midship sections, as I mentioned before. So this section is view is really important, and this procedure requires to treat the whole ship structure as a single beam. And using the simplified Euler-Bernoulli relation beam equation from Euler-Bernoulli theory, the strength can be calculated for the longitudinal bending. The Euler-Bernoulli equation describes the relationship between the deflection in the vertical dimension against the applied loading. So it is like this, Euler-Bernoulli equation. Uh, uh, so here, this is distributed loading. It's like then it's Newton per meter. It's like pressure, but pressure is like Newton per force per area, but this is like force per length. For example, in this picture, we can apply distributed loading like this. And professor was showing the video, for example, about the net distributed loading between buoyancy and the weight. So this is kind of that. And this is the vertical deflection in this picture. It's like in this direction, deflection of the beam. And these are this is the property of the section. So usually this Young's modulus is the property of material, so usually it's constant. And this one, for a given cross section, this is also constant. So usually we can write this relationship as this. This is a vertical deflection of the beam. So usually, as I said, this is material property, and this is given for the cross section. So usually this term is constant, so we can put it outside of the differentiation. Yeah. And so first, we have to find first of all, we have to find the neutral axis. we find the neutral axis, and then we have to solve for the moment of inertia. Inertia is given by this. Uh, yeah. So this is the width of the cross section. It's vertical, horizontal, and this is the height. So this is like the cross section in that direction, and this is the area of the same cross section, and this is for the vertical distance from the neutral axis. Yeah, and then so we can with these relationships we can determine the uh, moment of inertia, uh, and we can find ultimately we can find the strength uh, strength parameters of the beam. So Euler-Bernoulli equation is really important here. Uh, the worst case combination of loads. So in order to predict maximum bending moment, so what are the loads? It's usually the weight and the buoyancy. So in order to determine the maximum strength ability, we have to determine the worst case scenario for loadings. So we can draw the curve that shows weight per foot of the fully laden ship at each point. So this is essentially the net. We have to draw the force distribution for the beam per unit length. And then we determine the net distribution. So here like can also be distributed loading, and we determine the net, and from there we can calculate the bending moments. So this is kind of what I said. So we can draw the curve, which is drawn by these forces, and this is like the net distribution. So here we have to introduce new terms. They are sagging and hogging. They describe the shape of a beam or similar long object when they are under when the loading is applied. Hogging describes a condition when the middle part, when the beam curves upward in the middle. And the sagging condition is given here when the middle part is curved downward. This is sagging, and this is hogging. So these kinds of distributions can be described by these wave profiles. So this is one particular one, trochoidal wave. What is trochoidal wave? A trochoidal wave is an exact solution to Euler equations for periodic surface gravity waves. Euler solution for periodic gravity waves. What is a gravity wave? Is when in the fluid or in the wave in the fluid or between the two media, atmosphere, for example, air and water, and between the interface between two fluids, there is this restoring force which tries to return the system to equilibrium, and the restoring forces are gravity and buoyancy. Trochoid itself, the definition of trochoid comes from the circle. So trochoid is a shape that is described when a point on a circle kind of follows this curve when the circle itself is rolling along the line. It really looks like a sinusoid, but for small amplitudes, it really looks like sinusoid. But you can see the sharpening for the case of the amplitudes are like more steep and sharp than compared to sinusoids. And for larger amplitudes, this difference can be seen even more. Um, so uh, we discussed sagging and hogging, and this kind of distribution can be drawn with a graph. This is called knuckle 3 segment envelope, considering both hogging and sagging. And from the graphs, it can be seen that the maximum moments usually occur uh, within the half length of midship section. So we mentioned before that midship section, especially the half length, is really important for strength considerations. So this is why. Mm. Then maximum stresses. Yeah, I think we had this discussion. Um, uh, there is also this factor of safety. So when we have, okay, we determine the maximum strength, but then we also have to know, uh, we have to ensure that the shape will be safe. So we have to introduce this kind of reliability factor, and this is called factor of safety. So there are several types of actually there are many types of factors of safety, but usually um, uh, okay, factor of safety essentially expresses how much stronger a system is than it is required for it to be for an intended load. And one definition is called realized factor of safety. It's when you divide absolute strength of the beam to the actual applied load. The larger the value, the better. And the second, one more is a required factor of safety. It is given by imposed by the law, standards, and so forth. Uh, Stiffness of the material. So this is about the strain. So this is Hooke's law in stress strain form. So how far a beam will deflect? Actually, we can determine from here. But this relationship, if we have other given values like stress and we know material, so we know Young's modulus, so we can determine strains. And section modulus. Uh, for structural safety, we should not allow the most highly stressed parts of the beam to become overstressed. Yeah, so structural parts that are farthest, as we mentioned before, from the neutral axis are deflected the most, are stressed the most, and so, because of the Hooke's law, they are deflected the most. So, and the section modulus is given by S equals I over Y. So Y is the distance from the neutral axis, and Y is the uh, second moment of area. So this section modulus is a parameter that describes the overall measure of beam's ability to sustain a load. Optimum weight distribution. So these are kind of tips for better weight distribution for the material under stress. So strongest materials should be farthest from the neutral axis for the given reasons, and strongest materials in those components should for parts that run continuously, again the material should be strong, and in order to maintain the maximum strength, uh, the midship half length also should have the stronger material and thicker material.